So section 8.3 deals with scientific notation. And I know you've seen scientific notation in the past, especially in 7th grade. So hopefully a lot of this is a review for you. If not, you'll be pros by the end of this. So, real quick, our lesson opener actually just deals with abbreviations. So LOL, we know is laugh out loud, JK, joking, or just kidding. I've never seen this next one before. Maybe you know what it is, but you've got to be kidding me. Another one I'm not familiar with, you kids know the lingo though, so too good to be true, and then ASAP, as soon as possible. So scientific notation, just like all of those abbreviations, is just a way to write numbers more efficiently. Because if you take a look at some of these numbers, like the estimated number of atoms in a 154-pound human body, well, that's a lot of them, and that's a crazy amount of zeros to write. Same thing with the mass of an electron. Teeny, 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 tiny. Loads of zeros. Not very efficient way to write these numbers. So we use something called scientific notation. And our number is written in scientific notation when it is expressed as a product in the form of a times 10 to the nth power, where your a is going to be 1 or bigger, but less than 10. So a is greater than or equal to 1, but a is less than 10. Which means it could be a decimal, but that decimal value, it can be more than one digit, but the value itself has to be in between 1 and 10, or it could be 1. And of course, when we're multiplying by that 10 to the n power, the n tells us how many zeros we are adding to it. So for instance, this number, we have 4,200,000. Well, if we count over to replace our decimal where they've put the arrow, we've counted over 6 places. So since the decimal point moves 6 places to the left, we have 4.2 times 10 to the 6th. And you can see here, we have 4.2, which is a value that is greater than or equal to 1, but less than 10. Likewise, we can go the opposite direction. And when we go the opposite direction, since the decimal moves 5 places to the right, we're going to use a negative exponent. So 6.7 times 10 to the negative 5th power. So if our number's getting, if we have a tiny number and we're moving it so we end up with our decimal giving it a larger, like 6.7 is larger than 0.000067. So this looks larger, but our exponent has gotten smaller because now we're into negative exponents. So 29,500. It says move the decimal point 4 places to the left, because 1, 2, 3, 4, we want to end up with 2.95. So it'll be 2.95 times 10 to the 4th. So I'm going to keep saying this, our number is going to get bigger or smaller. Our number itself, the value isn't getting numbers or larger or smaller, but we're writing it bigger or smaller. It looks bigger or smaller. So when we say 2.95, 2.95 appears smaller than 29,500. So our number has gotten smaller. That means our exponent got larger, so we have a positive 10 to the 4th power. Example 1b. This time, going 1, 2, 3, 4, 5, 6, 7, 8. So we're moving at 8 spaces. Now, like I said, our number as it isn't changing, but the way we're writing it is changing. So we're writing it as a larger number. We're writing it as 4.3 instead of this teeny, teeny, tiny decimal. So since our number, I'm going to put it in quotes here, our number appears larger now, that means our exponent needs to be smaller, so we're going smaller than 0, so it's a negative 8 places, so 10 to the negative 8th. Example 2a. 2.1 times 10 to the 5th. So to express in standard notation, we move the decimal 5 places to the right. So we just end up with 1, 2, 3, 4, 5. We fill these in with zeros. We end up with 210,000. Example 2b, to express this in standard notation, we move the decimal point 6 places to the left. So we're going 1, 2, 3, 4, 5, 6. There's our new decimal place. We fill these in with zeros. And that's what we end up with. So products, powers, and quotients can all be calculated in scientific notation. Be sure to write the results of such calculations in correct scientific notation. So sometimes you might get an answer that ends up being like 32.8 times 10 to the 4th or something. Well, this isn't scientific notation because 32 is larger than 10. So we'd have to do 3.28 times 10. Well, our number looks smaller now, so our exponent's going to get 1 larger, so 10 to the 5th. So that's what they're saying when it says be sure it's incorrect scientific notation. We have to look at our final answer and say, wait a second, is this a value that's greater than or equal to 1, but smaller than 10? So example 3a, this is on page 340. We have 7.5 times 10 to the negative 5th power times 2 times 10 to the 3rd power. So what we're going to do, we're going to separate out sort of our regular values from our scientific values. So first up is our regular values, 7.5 times 2. And then we'll take care of our scientific notations, or the numbers with our exponents. So first, 7.5 times 2 is 15. Keep that in mind, that's 15. And then whenever we're multiplying like bases with exponents, we know that we add the bases. So we have 10 to the negative 5th plus 3, which will be 10 to the negative 2nd power. So we have 15 times 10 to the negative 2nd power. But are we done? No, because 15 is not between 1 and 10. So we're going to have to move that decimal over. So we're going to move it over one place. Our number is appearing smaller because it's going to appear as 1.5 instead of 15. So since it's getting smaller, this is going to get bigger. So if it's negative 2, we're going to move it up 1, so it's going to be 10 to the negative 1st instead. And they show you the math on how to do that. It's a whole lot easier if you just remember your number looks smaller, exponent gets 1 bigger. You end up with 1.5 times 10 to the negative 1st power. What they were doing here, they're just saying we're multiplying it by another power to move our decimal place, which is how we ended up with the 10 to the negative 1st. So example 3b. This time we're raising a power to a power, or a quantity to a power, so we're going to have to have 1.2 squared and 10 to the negative 4th squared. So 1.2 times 1.2 is 1.44. When we're taking a power to a power, we multiply these, so we have negative 8. So we have 1.44 times 10 to the negative 8. Are we done? Yes, of course we're done, because 1.44 is between 1 and 10. Example 3c. We have 2.4 times 10 to the 7th divided by 6 times 10 to the 2nd power. So we should go ahead and set these up like a fraction so we can deal with each part by themselves. So we have 2.4 over 6 times 10 to the 7th over 10 to the 2nd. Well, when we have 10 to the 7th over 10 to the 2nd, that's like 10 to the 7th minus 2. We can divide this out. 2.4 divided by 6 is 0.4, and 7 minus 2 gives us the 5th power, so 10 to the 5th power. So is this done? No, because this is not equal to or greater than 1. So we're going to have to move our decimal over once. So now our number is going to appear as 4, which is going to appear 1 larger. So we're going to make our exponent 1 smaller, so it'll be times 10 to the 4th. Or you can see what they do is they multiply by one negative power to make it 1 smaller. So we end up with 4 times 10 to the 4th. So either way you do it, whether you want to write out the math for it, or you just remember If your new number appears bigger, your exponent gets one smaller. If your new number appears smaller, your exponent gets bigger. So before adding or subtracting numbers in scientific notation, make sure that both numbers are expressed using the same power of 10. So let's take a look at that. All right, so we're adding, so that means we have to have the same power of 10. In this case, we do. These powers of 10 are the same. We have 10 to the 6th and 10 to the 6th. So that means we can go ahead and add 2.3 plus 5. We'll get 7.3 times 10 to the 6th power. This would be like writing it out. Whatever, 2, 3, let's see. 1, 2, 3, 4, 5. And then 5. 1, 2, 3, 4, 5. Whoops, forgot one. It'd be like just writing these out and then adding them. So 7, 3, 0, 0, 0, 0, 0, and then moving them back to scientific notation, which is why they have to be the same, so that they are lined up when we are adding these things together. So they have to be the same power. 4b shows us an example that are not the same powers. We have 10 to the 5th and 10 to the 4th. So we're going to have to make them the same powers before we can do anything. So we could go either way on this. We could either change them both to 10 to the 5th or both to 10 to the 4th. In this case, they are changing them both to 10 to the 5th. If you want, go ahead and pause it and try changing them to both 10 to the 4th and see if you get the same answer. So how did they get from 10 to the 4th to 10 to the 5th? Well, our exponent has to get one bigger, so our number is going to appear one smaller. So we end up with 0.47 times 10 to the 5th. Now we can go ahead and subtract, because we have both 10 to the 5th powers. So we're going to take 5.4 minus 0.47. And we get 4.93 times 10 to the 5th. And are we done? Yes, because it is greater than or equal to 1 and less than 10. So these are our metric prefixes and the powers that go along with them, along with their values. I would go ahead and throw these in your notes because chances are you're going to see them again. Also, word problems, and just for future reference, this is always good to have. I know it's easy to Google stuff like this, but it's also really nice to just have it right at your fingertips whenever you need it. You'll notice the micro symbol is a little funky too, so make sure you have that written out correctly whenever you copy these down. And then moving on, last one, example 5. So the mass of Earth is about 6 times 10 to the 24th kilograms. The mass of Mars is about 6 times 10 to the 23rd kilograms. And the mass of Jupiter is about 2 times 10 to the 27th kilograms. What is the difference in the masses of Earth and Mars? And approximately how many times more massive is Jupiter than Earth? So, first one. What is the difference in the masses of Earth and Mars? Well, we're just subtracting. The problem is the fact that one is given to us in 10 to the 23rd and one is given us to 10 to the 24th. So what they're doing here is they're making them both 10 to the 24th. So to make our 23rd to the 24th, our exponent goes one higher, so our number has to appear one lower. So we end up with 0.6 times 10 to the 24th. Now we can go ahead and subtract. 6 times 10 to the 24th, remember that was Earth. And Mars. And we get 5.4 times 10 to the 24th kilograms, where we can conclude that Earth is about 5.4 times 10 to the 24th kilograms more massive than Mars. 5b, approximately how many times more massive is Jupiter than Earth? So when we are saying how many more times, we're actually dividing. And so we're just going to set it up like a fraction and deal with each part. So our kilograms cancel out first of all. And then we have 2 over 6, which reduces to 1 over 3, and 10 to the 27th divided by 10 to the 24th. We can just subtract those. And then we'll want to write our decimal as our fraction as a decimal. 1/3 is 3 repeating, times 10 to the 3rd, because we have 27 minus 24, but this isn't in scientific notation yet. We're going to have to scoot this over 1, which means we're going to drop our exponent down 1, so we'll have 10 to the 2nd. We're going to round it, say about 3 times 10 to the 2nd, or Jupiter is about 300 times more massive